Okay, Science on Screen is a program funded by the Alfred P. Sloan Foundation and administered by the Coolidge Corner Theater in Massachusetts. It partners with independent cinemas across the country to present series of films, classic, cult films, documentaries that are somehow partnered creatively with science.
We all work at Western. I teach physics and astronomy at Western Washington University, and my colleagues here, Amites and Stephanie, teach math. And the reason I'm here, I know a little bit about math, not that much. They know way more about this than I do. But the reason I'm here is I'm also the host of Spark Science, which is a science talk show where we try to basically humanize science, try to make people not so scared of it. And I'm going to be able or try to kind of guide the discussion and ask questions. And one of the questions I ask on my show all the time is, how did somebody get into science? What sparked their interest into science? So before we even get into this, I'm going to try to humanize us and talk about, oh, can you push the... And that's Studio Ghibli stuff. Don't ignore that. That's my screensaver. So I'm going to talk about why we all kind of got into science, and I'm going to let them go first. I like space. That's why I got into science. So I'm going to let them go. So I'm going to ask Stephanie first. So why did you pick math?
I guess I sort of feel like I didn't have a choice. It was always my favorite subject from when I was sort of yay high, and it was always
what five?
Well, I don't really know. Certainly elementary school.
Okay.
It was always what I was kind of best at.
Yeah.
And then I sort of, when I got to college, I thought, well, I should try some other things. So I took general chemistry and really, really hated labs. And
no offense to our chemistry colleagues.
No offense to chemists, but I was not a chemist. So I thought, well, I'm just going to keep on with the math. And then I sort of fell in love with number theory in college, and then went on to study it in grad school.
Wow. And what did you study real quick?
Yeah, so actually I went to the University of Illinois for grad school, which has a long tradition of number theory research, and I sort of landed in sort of a hotbed of Ramanujan study because Bruce Barron, who's one of the longtime professors there, he's retired now, was one of the preeminent Ramanujan scholars, and he actually spent most of his academic career publishing volumes of work based on Ramanujan's notebooks. So Ramanujan was sort of famous for keeping these notebooks where he recorded all these amazing results but not really proving anything.
Which we'll see in the movie.
Which we'll see in the movie, and we'll talk about maybe a little bit later. Yeah. And so Bruce, together with many collaborators, has, many mathematicians since that time have been working on proving all these results, and remarkably, most of them are actually true. And so he has been compiling these volumes of sort of line by line, the notebooks with justification for all of the work.
That's amazing. And when you were this high, you were in Seattle?
Yes, I grew up in Seattle.
Okay. Mm-hmm. So you're a Washingtonian.
Oh, yeah.
Yeah. All right. Amitesh, do you want to tell me why you got into math?
I was actually inspired by the books written by two of the characters in this movie. So just in order to explain it, I can also explain something about the setting in the movie, because it ties in with how I got into it. So that's Ramanujan. And on the next slide, you can see Trinity College, Cambridge, this famous and amazing place. The bottom slide is a photograph from about the year 2000. The top right is from about the year 1900, and the top left is an engraving from 1798.
And for our listeners, I'm going to take this audio for our show later, but for our listeners, there is really no difference between any of these pictures. And when Amitesh told me that we saw the movie a little earlier than you, I'm sorry, and we saw that it didn't change at all, and he kept on saying, this looks exactly the same. Mm-hmm.
Yeah, you could almost spot the difference. I mean, I think I noticed a couple earlier. They have a saying in Trinity, which is that change is good and no change is better. And, so as an example of that, the famous movie Chariots of Fire, I don't know if many of you have seen this movie, Chariots of Fire, about two sprinters. A key scene, the Great Court Run, is set in Trinity, but it wasn't filmed in Trinity. They didn't have permission. But they did have permission to shoot this movie. Probably the most famous alumnus of Trinity College, Cambridge, was Sir Isaac Newton, who's on the next slide. And you can see there, there he is with Neptune, and his law of gravitation and his laws of motion. Really absolutely groundbreaking work, set the stage for modern science in the late 17th century with his book Principia Mathematica. Besides discovering the laws of motion and gravitation, from which he derived Kepler's laws of motion and showed the effect of the moon on the Earth's tides and other things. He also discovered calculus, discovered or invented calculus. And at the same time, in Germany, Gottfried Wilhelm Leibniz also discovered calculus. And this later on led to a bit of dispute between the two men and their followers, between Newton in England and the followers of Newton, and Leibniz in Germany and the followers of Leibniz. And one of the consequences of this was that English mathematics was cut off from the continent for around 200 years. England had some great physicists like Maxwell, who also went to Trinity in that time, but mathematically, relatively speaking, it was isolated, and that continued for 200 years until these two guys came on the scene around 1910. They had a famous collaboration, which is the stuff of legend, really.
And for our listeners, it's Hardy and Littlewood.
G.H. Hardy, yes.
These two guys.
G.H. Hardy and J.E. Littlewood.
Yeah.
And they also both went to Trinity. They wrote 93 papers together, incredibly influential. People still mine them for ideas. At the time, it was unusual to collaborate in mathematics. So one of the interesting things is that now it's the norm. Then it was rare. And this is probably the first famous one in mathematics. And not only did they collaborate, they also maintained correspondences with mathematicians from other countries. So in Denmark, in France, in Germany, and also in America. So really they put mathematics, or put England and Cambridge back on the mathematical map in a big way. Towards the end of their lives, they both wrote books emphasizing the aesthetic component of mathematics as opposed to its practical applications. And Hardy's book, which I really recommend, is called A Mathematician's Apology, and it makes the case for the artistic side. Two famous quotations from this book are, "A mathematician like a painter or poet is a maker of patterns," and "Beauty is the first test. There is no permanent place in the world for ugly mathematics." So that's a very poetic book, actually. It's a sort of a justification of his life's work. It's slightly depressing. Littlewood's book is, for reasons you should read it and see why. Littlewood's book is a lot more uplifting. It's called A Mathematician's Miscellany, and it's a miscellany, and it ranges from anecdotes to longer essays. So there's a beautiful one about the discovery of Neptune. But these are two books, and both of them I recommend to you if you're interested in this.
And when did you read them? How old were you?
Well, I was a teenager. I was 15 when I read them, and so I read. That was the first time I heard about Ramanujan, and I didn't know there were any Indian mathematicians actually.
At all?
At
You were
all?
just like-
Yeah, I didn't. I was incredibly ignorant, and so. But then I thought, well, Ramanujan is an Indian mathematician. Maybe I'd be a mathematician, And then later that, just by coincidence, later that year, we had a family trip to India, and I begged my parents, "Can we go to Madras? I want to see where this guy grew up and lived and everything." And so eventually they said yes. And so me and my dad and my brother travelled to Madras.
So you're 15 when this is
I
happening.
was 16 by
16,
this time,
okay.
yeah. And I think my dad made some interesting phone calls because we were hosted by Professor Rangachari of the University of Madras, and he drove us around and he took us to the library, where I held Ramanujan's notebook in my hand. 3 red books.
Wow.
And then also he drove us to meet Ramanujan's wife. So I met Ramanujan's wife, who was in this movie. She was 90 at the time. She lived in a small 2-room house. One of the rooms was like a shrine to her husband. And that was a life-changing experience for me. And a few months later, I applied to Trinity College, Cambridge, and was lucky enough to get in. So that's, I guess, my second connection with the movie. So the longer answer.
No, I love that
Long
story.
answer.
That's wonderful. So, the reason I ask these questions, I don't have a awesome story like that. So that's why I just said I like science and I like space. But the reason I ask that is just because once we know the stories of these scientists, and that's what this movie's about, once we humanize these scientists, then science becomes less frightening. At least that's what I think. Maybe I'm totally wrong. I don't know. But now that we kind of got a grasp of kind of the history of what's going on with Trinity, I want to kind of give it over to Stephanie, and she's going to kind of take us through some of the math that's happening in this movie, which is really interesting and groundbreaking.
Yeah, so I wanted to talk a little bit about the math that happens, that you'll actually see in the movie, that they're working on in the movie, but then also talk a little bit about how it has influenced mathematics since that time, because it's really had a very profound influence. And what you see in the movie is just mostly working on 1 or 2 problems that Hardy and Ramanujan worked on during their time at Cambridge, but actually they did a large volume of work. You mentioned how many papers they published together. And so I wanted to give an idea of sort of how Ramanujan's work is still influencing mathematics today. So here's a definition. So they make this definition in the movie, but it goes by really fast. So I thought we would spend a minute and think about it here, because actually the origins of this problem that they're going to be working on are pretty easy to state and start thinking about. So it starts with just this definition. So you guys know what a positive integer is, right? 1, 2, 3, 4, 5, 157, 6,924. Positive integers.
That's my favorite one.
That one right there. So we can think about how we might take a positive integer like, say, 4, and write it as a sum of other positive integers.
So
Pretty simple.
So sum being addition.
So like 3 plus 2 equals 5. So that's one way to write 5 as a sum of 2 positive integers. And then we're just going to count all the ways to do it. So one of those ways of writing it is called a partition. So 3 plus 2 is a partition of 5. And then we want to just count all of the ways that we can do that. So here's an example. So here are all the partitions of 4.
Which they actually go through, I think, in the movie, right? They give this example.
I think this is sort of everybody's first talk in partitions uses this example pretty much. I've seen this example about 100 times. So here are the partitions of 4. So you've got 4, and you got 3 plus 1, and 2 plus 2, and 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. So notice that I haven't written 1 plus 2 plus 1 up here, because I'm not going to count that as a different partition than 2 plus 1 plus 1. So for the purposes of what we're doing here, we think of if we rearrange the terms in a given partition, that doesn't make it different. Okay? So we count this as 5 partitions of 4. And so, well, mathematicians like patterns, right? So we have this definition. We can play around with it. We could compute this number, this partition number, for a number of small integers n, and kind of see what we come up with. But before too long, we're going to start asking ourselves, because we like patterns, well, can we find some nice formula for p of n, the number of partitions of an arbitrary integer n? So, well, we can sort of start with simple examples. So can you guys all agree that p of 1 is 1? There's only one way to write 1 as a sum of positive integers, because it's just 1 itself. So what's p of 2? 2, okay, good. And what about p of 3? Are you sure about it?
4. You want to...
So what are they? There's 2 plus 1, what else?
1 plus 1 plus 1.
1 plus 1 plus 1, and what else? Just 3 itself, that counts too. So there's 3 of them. Okay, and then we already looked at p of 4, that's 5. Ooh, what about p of 5?
Do you want to let them discuss amongst
Oh, yeah,
themselves? It's
yeah,
like a class.
absolutely. Take a
Discuss
minute and
amongst
think
yourself.
about it.
Yeah. Talk to your neighbor. See, this isn't scary. This is fun.
It's scary for me.
This is like my class. You see like a lot of people talking and then a few people just like, no, I'm not going to do this. It's not what I bought a ticket for.
Should have got cards, flashcards.
Flashcards, yes.
How long should we give them? They're
All
still
right.
thinking.
Who wants to guess? All right, yeah.
If it's Fibonacci, it's going to be.
If it's
Ooh.
Fibonacci, it's going to be
We
8.
have a guess at a pattern already. So you're guessing that the numbers are going to continue like the Fibonacci sequence.
I want a different, somebody who doesn't think 8.
So he thinks 8 is next.
Any number that isn't 8? Yeah,
6.
he says 6.
6. Did anyone get a different number than 8 or 6? 7. How many people got 7?
Okay, here we go.
Ready?
Yeah. Oh, that was a hint already. You're like, how many people?
I know. I telegraphed that one. Okay, so now can we guess at a pattern? What do you think P of 6 is going to be?
Ooh.
Without trying to work it out, but just maybe guess.
Yeah, let's just guess.
Because,
Someone says 9.
9, all right.
Ooh. That pain is learning. That's what struggle. That's what I tell my students. Struggle is learning.
All right, so
like
any
working
guesses
out.
at P of 7? Yeah, what do you think? 13. Ooh. So they're not Fibonacci numbers, and they're not even prime numbers anymore.
Uh-oh.
Okay.
That's why this question was hard.
Yeah, it gets hard. So this is actually why this function is interesting, because it actually doesn't have a really nice, obvious pattern. So they're not even all odd. This one's 22. And they get kind of big kind of fast. And already at this point, I wouldn't want to sit down and work out all of them by hand. So P of 10 is 42. What's your guess about sort of order of magnitude? Like how big would P of 200 be? I mean, I know this is based on nothing but pure guess, but just guess. Wait, I heard 2,000, I heard 600. 5,000. So kind of on the order of the thousands, that many? Do you guys all kind of think that? It's a reasonable guess. I haven't given you that much data to go on. Yeah.
And this number, remember this, and you're going to all feel very, very smart as you're watching this
Yeah,
movie.
you're going to see this number in the movie, and you're going to be like, aha, I know where that is. I know where that comes from. So what is that, 3 trillion something? Do I have my
Millions,
zeros?
billions, trillions, yeah.
3.9 trillion. So huge numbers, right? So how do you think they calculated that? They certainly didn't just write down all of the partitions of 200, because they would never, I mean, even if they had enough time, I mean, who could make sure that you actually got all of them? Because there's just so many. So we would like some sort of a formula, or people that were thinking about this at the time would like some sort of formula for P of n, but it doesn't obviously follow any nice pattern. So it's actually sort of turns out to be a hard problem to find a nice general formula for P of n. So that was what people started thinking about. So this is a formula. It's a recursive formula, which means that it defines P of n for a particular n in terms of P, the partition number for smaller values of n. And this follows from work of Euler in the 1700s. And so let's see, P of n is P of n minus 1. It's sort of the sum of two numbers minus two more numbers plus two more numbers. And there's actually a pattern here that continues. Does anyone happen to know what these numbers are? 1, 2, 5, 7, 12, 15? That's kind of tricky.
I mean, they're similar to the ones we had up there before, the partition numbers.
Well, yeah, except 12 wasn't a partition number. So they're actually something called generalized pentagonal numbers. Woo.
I have no idea what those are.
Yeah, I'm not going to spend time explaining what those are now, but there is a pattern to these numbers.
Oh, I do want to take a quick second to say that in math and in physics, Euler, spelled E-U-L-E-R, is like this long, long thing where everyone's pronouncing it wrong, and it just comes up over and over and over again. Mm-hmm. So if you want to seem smart to your neighbors, you can bring up his work and actually pronounce his name properly. I think it would impress a lot of physicists and mathematicians.
Oh, yeah.
Yeah. Mm-hmm. Just heads up, tip for you.
So let me say one more thing about this formula, because it's a little funny. So the formula goes on and on and on, but if you notice, if you do this for a particular n, like we're going to do it for n equals 11 in a minute, pretty soon the numbers inside those p's drop to be below 0. So we just agree that p of a negative number is 0. So in that way, the sum actually just ends after some number of terms. So for example, for p of 11, it's just 4 terms, P of 10 plus P of 9 minus P of 6 minus P of 4, and those are values we already saw. We plug them in and we get 56. So this is one way to calculate partition numbers that's better than just writing down all the partitions, certainly better, although it's still kind of tedious for big numbers. So it's actually maybe surprising that someone actually had the patience to crank through this formula for fairly big numbers, in fact, all the way up to 200. So that is what this guy did. So Major Percy McMahon. So you're actually going to see him in the movie too, and you'll know it's him because he's played by the same guy who played Jack Sparrow's first mate in the Pirates of the Caribbean movies.
Yeah. When Stephanie pointed that out, I was like, oh my God.
Regina was like, who's that guy? Who's that guy? And
Yeah.
all of a sudden, halfway through the movie, I was like, oh, I know who it is.
Yes, it was amazing.
It was cool. Anyway,
Yeah.
so he was a major in the British Army, and then he retired and devoted himself to mathematics and became a fellow of the Royal Society of London.
So he was in the Navy?
Some branch of
So that's why when he was in the Pirates movie, got it.
Oh, there you go.
It all makes sense. Go ahead.
And so he was really interested in sort of combinatorial things, counting problems. And so he cranked through that recursive formula by hand and calculated tables of partition numbers all the way up to 200. And those were actually really valuable for people like Ramanujan looking at those tables of values later and trying to figure out patterns in the partition numbers. So he did this by hand. But still, you can imagine that was pretty tedious. And so there was still this desire to find some type of a better formula for P of n. So this is one of the big contributions that Hardy and Ramanujan made together. Ramanujan had proposed this formula for P of n, and then he was actually able to formally prove it with Hardy during their time at Cambridge. So it's an asymptotic formula for P of n, which means it's not an exact formula, but roughly speaking, it means that these two functions, P of n and this funny function on the right, sort of grow at the same rate as n gets really, really big. And you'll notice there's really sort of interesting things in that formula on the right. There's square roots, and there's pi up there, and there's e, which is another famous mathematical constant. And it's really sort of surprising that that formula would have anything to do with integers, because if you plug in an integer n to that formula, you're certainly not going to get integers. But it turns out that it actually is a good asymptotic formula for P of n.
Well, and once he got this, I mean, when it has like natural numbers like e and pi, I mean, that seems like it means something, right? Like for like a mathematician, that's like really awesome.
Yeah, absolutely. I mean, when you're a mathematician and you come up with a formula that sort of has these really beautiful constants in it that are really important, you sort of figure like you've got it right somehow.
Right.
Yeah, that's kind of the goal is to find something that feels right, and something this beautiful probably felt right to Ramanujan.
But it's also mysterious, right? I mean, like, what do these numbers have to do with circles and everything?
Yeah, so one of the important things about this formula was not just that they were able to prove it, but that to prove it, they had to develop this new method called the circle method, which ended up having widespread applications to various other problems in analytic number theory. And so throughout the early part of the 20th century, this method was used to prove a lot of other results besides this one.
Can either of you kind of give just a very brief explanation on why pi is so important to circles and stuff? I mean, like, well, it's super brief, but I mean, but it's yeah.
It's defined in terms of circles, and it shows up in the volume of a sphere. But the surprising thing is it also shows up here in a completely different context.
Right.
I mean, I defy anyone to explain to me intuitively why pi should appear here, or e for that matter, or square roots. And so that's the surprising thing, that you can have something from one branch of mathematics, it shows up in a completely different place, and it's very much against my intuition anyway.
So I want to go on now and talk a little bit about some ways in which Ramanujan's work influenced later mathematics. So here are some values of the partition number, and these would be kind of like the tables that McMahon generated of the partition numbers that Ramanujan studied. And he actually noticed a really surprising pattern among these numbers. So if I highlight these ones, so let's think about what these are. So in each sort of pair of columns, I've got n on the left and p of n on the right. So the n that correspond to the red numbers are all numbers 4, 9, 14, 19, 24, 29. So they're numbers that are 4 more than a multiple of 5. Does that make sense? Okay. So when you have a number n that is 4 more than a multiple of 5, then it turns out that the number of partitions of that number is, well, what do you notice about those numbers in red? They're divisible by 5. They all end in either 0 or 5, which means they're all divisible by 5. So that's kind of weird. And it turns out it happens again. If you look at numbers that are 5 more than a multiple of 7, then the partition numbers for those numbers are all divisible by 7. And again with 11. So numbers that are 6 more than a multiple of 11 have partition numbers that are divisible by 11. And this is kind of a sort of a strange pattern. And stranger even more so because it doesn't really happen again after those 3 instances. So here's a different formulation of what we just saw. And Ramanujan actually did prove these results. So this is written in the language of modular arithmetic, but really what it means is the number on the left, p of, say, 5n plus 4, that just represents all the partition numbers we're talking about, partition numbers of all numbers which are 4 more than a multiple of 5. And then the bit on the right, that part that says sort of the 3 lines, 0 mod 5, really just means that that number is divisible by 5. And the same for the second line, that those numbers are divisible by 7, and the third numbers are divisible by 11. So the remarkable thing is that not only did he prove these, but he conjectured that these were the only 3 congruences, that's what we call these things, congruences, of this form. of the form where you're dividing by a prime number L, and you're looking at numbers that are some beta more than a multiple of L. But he conjectured this back when he was alive. It wasn't proved until 2003. So he was really sort of ahead of his time in terms of his insight for things. In fact, it was proved at the University of Illinois when I was there by my thesis advisor, Scott Algren, and another postdoc, Matt Boylan. And it used a lot of modern mathematical machinery to prove it. I saw Ramanujan described as a great anticipator. He really anticipated things that were sort of far ahead of his time in terms of mathematics, that took everybody else, decades and decades to build the machinery to be able to prove rigorously. So here's another result. So it turns out that although these are the only 3 congruences of this type, if you relax what you mean by these congruences a little bit, if you generalize this a little bit, it turns out there's a lot more. So if you keep thinking about dividing these partition numbers by a prime number, but instead you just look at partition numbers of any number of the form an plus b, where a doesn't have to be that same prime L anymore, then there's actually lots and lots of these among the values of the partition function. In fact, this says there's infinitely many pairs a and b such that p of an plus b is divisible by L. Okay, so this was actually proved, again, much, much later in 1999 by Ken Ono, who is very much involved in the mathematical work of Ramanujan, continuing on Ramanujan's legacy and proving things about the partition function. He was also the math technical advisor on the film. Oh, oops, I forgot this part. So here's an example of this. So they're not necessarily very easy to find. This is sort of a simple version of what I'm talking about. So the number a is 13 times 59 to the 4th. And then you have to add this other big number. And then those numbers are divisible by 13.
And then it totally works out.
Yeah, it totally works out. But you wouldn't really just sort of come up with this unless you were really looking computationally for these things. So there are a lot of them, but they're a little bit obscure when you actually try and write down an example.
And I mean, these weren't done by brute force, like you were saying. They were like computer simulations and programs going through this.
Yes, absolutely. So I mentioned Ken was the technical advisor on the film. So here's a picture of him working with Dev Patel, who plays Ramanujan in the movie. And you'll actually recognize this setting when you see the movie. And,
Spoiler alert.
Spoiler alert, they do math on this chalkboard in the movie.
Yeah, that one specifically.
Yeah. And I got a chance to talk to Ken a little bit about his time. He actually went to Trinity College when they were filming there and worked on set with these guys, which was really cool. And so he said that most of the mathematical writing, I think, like this, that you see in the film is actually Ken's writing. But he said also that the actors, Jeremy Irons, who plays Hardy, and Dev, who plays Ramanujan, really were interested in understanding the motivation of these characters and really kind of getting the details right in terms of their portrayal of mathematicians. Even though they didn't understand the mathematics very well at all, they were really trying to get at the heart of sort of the type of people these guys were, which is interesting.
He looks super happy to be there, Ken.
Yeah.
So, do you want to go into this?
Oh,
I
I don't want to take up all the time. I have a little bit more I could talk about, but if
no,
you want to...
I think we can. You go ahead and talk a little bit more, and then I wanted to ask more about like how can we talk about math to the public and also pop culture, because that's what this is.
All right. Well, I'll just mention a couple more things. So one of the ways in which Ramanujan's work was sort of ahead of its time is he conjectured all these things, and he wrote down all these results that he then didn't prove, and that really required the modern machinery of what are called modular forms to prove. And so these recent results that I mentioned, were proved using the theory of modular forms, which, although modular forms were known to Ramanujan, he thought of them in a different way, and the sort of the modern theory of them has really been developed over the last 50 years. And so if you're interested in what a modular form is, I have just a little slide that talks about it. So most of the functions that we think about when we learn math in high school or college are functions of real numbers. So the input value is a real number and the output is a real number. So I'm thinking of things like polynomials or trigonometric functions.
Or F equals MA.
Sure, yes, exactly. So modular forms are actually complex valued functions. So you plug in complex numbers. You guys have heard of imaginary numbers, like the square root of -1. So you can think about, in general, complex numbers, which include the real numbers, but also many more numbers. And so you plug in complex numbers and you get out complex numbers. That's sort of a weird type of function. And they are meromorphic, which there's a little definition up there, but really just that means that they're sort of reasonably well-behaved functions. And they have a lot of symmetry, and I'll say something about what symmetry means. So here's a picture of the sine function, sine of x. You may be familiar with this. And if you know a little bit about this function, here's a graph of it. The red thing right there is a graph of a portion of it. Everything you need to know about this function is contained in an interval of length 2 pi. In fact, it's periodic, we say, with period 2 pi. So there's actually 2 periods drawn on this graph right here. But if we looked from just the right half, from 0 to 2 pi, that contains everything we need to know about that function. That picture just repeats to the right and to the left as many times as we want. And so we could sort of say that a fundamental domain for this function has length 2 pi. It contains all of the necessary information about the function in that interval. So here's a fundamental domain for a modular form. So I mainly put this picture up here because I think it's really beautiful. But let me say a little bit about what it means. So here now, this isn't a graph of the function anymore of a modular form because that's really hard to graph because it's how do you graph complex numbers. But you could think of this as the complex plane, or the upper half of the complex plane. So think of this as like the input values of your function, of your modular form. And so the way that this is divided up into all these regions, I guess, there's one shaded up there in gray. Each of those you could think of as a fundamental region. So just like the interval, the real interval 0 to 2 pi is a fundamental region for sine, one of these regions, either the gray one or any of these other regions bounded by these blue arcs and straight lines, is a fundamental domain for a modular form. So everything you need to know about a modular form in terms of its values or its behavior would be contained in one of those regions in terms of input values for the function. And so the behavior of the function sort of repeats itself on all these different little segments of the complex plane, which is kind of cool and really pretty, I think.
Does this have anything to do with, what is it called? Where is it like broccolini? No, it's not broccolini. It's like patterns within patterns and fractals.
Fractals.
There we go. No. The answer can be no. It's fine.
Yeah, not really directly.
Okay, good.
No. Yeah. So let's see. I can't remember what's next. Oh yeah, so what does this have to do with partitions, sort of bringing things full circle? So modular forms themselves have sort of become ubiquitous in mathematics. They have lots of connections to not only number theory and algebra, but even things like mathematical physics. But the connection to partitions is that if you write down what's called a generating function for the partition numbers, which is right here. So what do I mean by that? Well, if you think about what all these terms are, the exponent on q is like n, and then the coefficient, the number in front of the q, is the p of n value that corresponds to that n. So like 5q to the 4th means there are 5 partitions of 4, and 11q to the 6th means there are 11 partitions of 6. So you can write down this, it's an infinite series. This was known to Euler. But it turns out if you define q in the right way, you essentially get a modular form. So you can use all of the modern machinery of modular forms and what we know about modular forms to prove things about this function, which in turn prove things about the partition numbers. So it's this really odd combination of using very analytic methods, things about complex numbers and really sort of heavy machinery to prove things about this particularly interesting sequence of integers. And you wouldn't really think that integers and complex numbers would have much at all to do with each other, but it turns out they're connected in this really beautiful way.
Awesome. So, I mean, that brings me to the point of like, is that another reason why both of you kind of went into math too? Just seeing these connections, seeing this beauty, which is what, like you were saying, like those books we're talking about.
Yeah, for me, definitely. I mean, it's the connections that are the surprising thing somehow.
Yeah.
Well, all the busy work is not interesting at all, right? It's the surprises, right? I mean, just like in
Yeah.
everyday life, it's the surprises, I think.
Right. Well, I mean, do you think that that's conveyed to the public properly? I mean, like this idea that math is beautiful and that there are these wonderful connections. I think, is that done well? I think it's done well in this movie and
Yeah.
sometimes in other pop culture. But do you think that it could be done better?
We're all trying to, I think, in our classes, but just
Yeah.
a little bit at a time.
Right.
I think it has this authoritarian image somehow that,
Yeah.
people trying to trip you up as well. It has that image as well, trying
Right.
to catch you out on sums,
Right.
which is the opposite of what we're trying to do. I think,
Right.
so.
Yeah, I think there's sort of this notion that math is sort of a kind of a list of rules that someone has devised that need to be either learned or
It's like a TV manual. Or
yeah,
like a VCR
yeah, sort of
manual.
rules to be followed, when actually it's a much more creative process, and people don't necessarily get a chance to see that if they're just kind of taking standard courses and not sort of experimenting on their own and playing around with things on their own.
Well, and that brings me to we thought of a couple questions before, and I'll definitely open it up to the audience to be able to ask a couple questions too once we kind of get to the core of this. And I think a couple of things is, this is all beautiful and this is great to find these connections, but how does any of this how can we spark public interest by maybe relating it to everyday life? Like, how do we do that? And how does maybe any of this or any hard math research relate to everyday life?
You had some examples.
Yeah, I mean, I think just the human side of it's very important. So all these names that you read about in books, and if you're a math student, you'll study mathematics by lots of famous mathematicians like Newton. But the human side of it is interesting because sometimes often people have difficulty learning mathematics, but the people who invented it also had difficulty getting the thing right. And so there's the human side of it. The practical applications are also very important. But they can be unexpected. So my favourite story is, I think, GPS receivers. So your smartphone has GPS in it. That wouldn't work without relativity theory, special and general relativity. And if you don't include the relativistic corrections, your position fixes off by tens, hundreds of meters. Relativity wouldn't work without non-Euclidean geometry, but Einstein wasn't interested, Einstein was interested in GPS, and the people who invented non-Euclidean geometry weren't interested in relativity. They were trying to prove Euclid's parallel postulate, so that goes back 2,000 years. So it's a series of sort of just, unexpected coincidences where someone did something, and then 100 years later it showed up in some completely different context. But the use of mathematics is undeniable. I mean, everywhere you go, you see mathematics in action, often to improve things rather than to design them. But still, I mean, it's everywhere.
Yeah, for every credit card transaction you make on the internet is based on number theory.
Mm-hmm.
Right.
The security of those transactions is
Prime
based
numbers,
on the difficulty of factoring numbers that have large prime factors.
Right.
Yeah.
Well, my favorite, we're going to see Ghibli again. That was my screensaver. My favorite is Michael Faraday, right? When he's playing around with, moving magnets and seeing that is actually going to create current, or the other way around, that, a changing magnetic field created, changing magnetic field created current, or moving current makes a magnetic field. I think somebody asked him, I think this was a famous quote, right? Like, somebody asked him, what good is that? What good is showing that these two things are related? And I think he said, what good is a newborn babe? I think that's what he said. Because he was a really nice man, though. He really was. Read some stuff about him. But, this stuff comes out of, we as scientists and mathematicians are very passionate about this work, and then, it's lucky that these things come out, too. Or maybe, I don't know, maybe it's important. Maybe it's going to happen anyway. I want to talk about how, we're going to see a little bit about in the movie about the culture of mathematics, and you talked about it a little bit. There wasn't a lot of collaborations. Newton didn't collaborate, which is why there was these two camps and there was this thing happening. But how has that changed in the last 100 years? And you kind of talked about it a little bit, but can you elaborate more maybe on that?
Yeah. Do you want to say something as well? I think people do collaborate a lot, and I think people have realised that it actually, if you collaborate with someone, then you can, you really typically complement each other. That if you're working on something by yourself, you make some progress, then you get stuck for a long time, then you make some more progress, then you get stuck for a long time. But you get stuck on random things, and so someone else would get stuck in different places. So where you would get stuck, then they can take over, and then where they would get stuck, maybe you can take over. And so, and people have realised it really does work, and it's fun. But for a long time, the culture was very different. I mean, if you look in the 19th century, there's very, very few joint papers in the 18th century.
And the 21st century conclusion of this or evolution of this is the polymath project. So there's these sort of massively online math projects now where people like sort of really eminent mathematicians like, I guess, Tim Gowers and Terry Tao are sort of organizing these group projects online where they pose a question and anyone who wants to can write in and add to the discussion. And they've proved results in written papers like this.
Absolutely, yeah. There was a blog post about 7 years ago, Tim Gower's blog, "Is massively collaborative mathematics possible?" And then within days of that, people took it up and then set up a sort of a collaboration wiki, and then it really took off. So that removes this sort of geographical barrier, so that you can, if you're interested in mathematics and you have an internet connection, you can just sort of contribute your ideas and collaborate with the world's best mathematicians, if you like. And so maybe that's the future. I don't know.
And that brings us to the point that's brought up in the movie a lot, this idea of, if you love math and you love science, is formal training necessary? And that's stuff that I think as professors kind of get the brunt of sometimes, that frustration, is formal training necessary? So I wanted to address that just before we went into the movie, because it's something that's just all over this movie.
Yeah, there's this sort of tension that you'll see in the movie between Ramanujan, who was he was incredibly intuitive, but he didn't have formal training in sort of particularly like sort of the Western mathematics way of verifying your work in a way that can be explained to other people so that they can understand why things are true, not just a formula, but how did you come up with a formula? Why is it the way it is? And so there's this tension between Ramanujan on the one hand wanting to just work with his intuition, and Hardy really trying to tell him that he has to be able to verify his results and explain them in the way that other people can understand them. Right. And it's sort of this tension throughout the whole movie.
Yeah.
I think another thing is in mathematics there's this tension between your intuition and being able to really check all the details. And even the best mathematicians, their intuition just leads them astray sometimes. So then you check some more details, you sharpen your intuition, then you go forward with your intuition again, then you check some more details. And so even Ramanujan's guesses were wrong. Some of them were wrong about prime numbers. But he certainly had a much better intuition than basically anybody. Right. So, yeah.
Yeah. Which is another recommendation for for collaboration, right? Because if you have to explain your work to somebody else, and then they can maybe find some gaps where you didn't know there were gaps before.
And you have two different intuitions.
Yeah.
So that's another thing. I mean, you think, I'm sure this is true. Your collaborator says, no, it can't possibly be true. What are you talking about? And then you talk about it, and then you come to the truth.
Right. So that's our answer to all of our students that are like, why do I have to show you why this answer is right? It's right. It's because you have to explain. Yeah.
Mm-hmm.
Yeah. That's how somebody can help you, like you were saying.
Well, and also, if you want other people to gain anything from your work, they have to be able to understand it. Otherwise, it just sort of dies with you. If you're the only one that understands it, then it's not going to help anybody else.
Right. Absolutely. And so I'm going to kind of just this is my last question, I swear, and then I will open it up to the audience. And it's
Oh, hello.
You're just gifted with all these images every once in a while.
Humanizes you, know?
It is. I'm very human. I think they all know I'm a human. But one last thing. I mean, have portrayal of mathematics gotten better over the years in pop culture? Like we've all seen this movie, and maybe there's like A Beautiful Mind, and there's movies about mathematics. Do you think that they've actually, in your opinion, gotten better portraying mathematicians, or can you think of ones that are just awful portrayals?
Yeah, I don't know. I think in general, as sort of movie making and TV making has become more sophisticated, they've started hiring, consultants like Ken Ono to get things right where they didn't do that before. I think with math sometimes there's sort of this kind of cliche of the absent-minded professor or the mentally ill person who is a genius at math, and so those are the sort of the stories that are told because I guess they're dramatic and interesting, but it's not particularly typical of mathmaticians.
Right. There's Jeff Goldblum in
Jurassic Park.
Yes,
yeah,
I just want to throw that in there.
Yeah. He was quite good at the time, I remember. But because the other ones had the complete stereotype, and he at least was sort of like eccentric.
He dabbles in stereotypes. Yeah.
But, I think they've got a lot better actually.
Yeah.
The movies. I mean, sometimes it doesn't need to be a good movie to inspire people, though. But the black hole, the Disney movie. There's a professor at the end, and that he's getting spoiler alert. You won't see it, and it's a very old movie. But there's this sort of, he's getting murdered, and this thing goes through all his calculations, and they spray all over the place. And I remember thinking that was incredibly inspiring. But I mean, but they got a lot better. I thought that the Imitation Game was very good, for example. So.
Yeah. So I'm with that. I love that visual. I'm going to open it up to questions. So, all right, Casey, I actually know you. So ask your question.
In the movie we're about to see, how does the depiction of actually doing mathematical research, either as individuals or as them working together, how does that actually relate to your experiences? What's it like for you when you sit and actually do theoretical number theory research, or when you sit down in your office and work together? Like, what's that process like compared to what we've seen?
Yeah.
So can you repeat that question? Just
Yes. So the question was, how does the portrayal of math work in the movie relate to our experience of math work in real life? So I think it's actually fairly good. I mean, you sort of see them, working at a chalkboard, sort of arguing about things, basically. I mean, arguing in a nice way. That's sort of what happens. I mean, honestly, it's a lot of either working at a chalkboard or whiteboard or on paper and pencil and, thinking for a while and writing some stuff and scratching it out and thinking again and talking to people and sort of arguing your position one way or another. And that's sort of what happens in the movie. There's this great, I don't know if you guys watch The Big Bang Theory, but there's this great clip from one of the episodes where two of the characters, they're physicists, but still it's the same type of thing.
One is an astrophysicist.
Right. So they decide they're gonna work. It's time to work. So it's just a montage of them staring at a whiteboard while Eye of the Tiger plays. And I like to think of that's how I work,
Do you have anything to add there?
There's a number of different ways of working, actually. I recently wrote a paper with two people, one in England, one in Japan, and so we were just rotating, so every 8 hours, and then we could communicate only in these small time windows, and I never met one of them, in fact, but it still actually worked quite well. So the normal thing is what you describe, I think, and what's in the movie. That's the usual thing, but there's, all sorts of things are possible.
You mentioned the one thing where he kind of comes in and throws his papers down.
Yeah, frustration is also possible.
Yeah. So there's a point where, anyway, it can be frustrating doing mathematics because you could sort of have what you think is a great idea, it doesn't work, or you can just be stuck for a long time. And so, yeah.
That's realistic in the movie, is what you're saying.
Yeah.
Totally, yeah.
Yeah, your question over there, glasses guy.
Sorry.
Murray,
Sorry.
yeah.
Murray? Okay, you know him. Okay.
The title, The Man Who Knew Infinity, why is that the title? It seems like a movie about cancer, maybe. What's the connection to infinity and
Well, it's actually the name of the book that the movie is based on.
By Robert Canigal.
Yeah.
So, sorry. The question was, why is the title The Man Who Knew Infinity? So go ahead, sorry, ask.
Oh, yeah.
Yeah, there's a famous book by the movie's based on a book by Robert Canigal, which came out about 25 years ago. Apparently very good. I haven't read it, but apparently everyone says it's a very good book. So.
And you have no idea where he got that title?
No.
Yeah, just leave the Kipling on. Any other questions? I think we got like 4 more minutes. Right over here.
How frequently do you find yourself actually working out ideas and trying ideas versus just staring catatonically at you?
Can you repeat what he just
Yeah,
said?
how often are we actually sort of actively working something out as opposed to being stuck, basically, is the question?
Yeah.
I guess it kind of depends on what you're working on and how many people you have to collaborate with. I mean,
And when you're not teaching?
and when you're not
grading?
teaching, yeah. I mean, it's of course we balance our research work with teaching work and other commitments at the university, and so we sort of find time for research where we can. Yeah, I don't know. It kind of depends. It's sort of one of these things where you can kind of be stuck for a long time and then like have an insight and kind of work like crazy and then kind of get stuck again. It's sort of hard to say how much of my time is spent in either state.
One thing that happens quite a lot is you think about a problem for a long time and then you think about it when you're going to sleep and think about it. You make no progress at all. It seems you're completely stuck. And then you're about to give up. And then suddenly you get an idea. And it's completely unpredictable. So math might be logical, but the process by which you discover it is who knows what it is, you know.
And also, I mean, in reality, you're potentially maybe working on a couple different projects at a time that are in various stages. So maybe you're sort of in the back of your mind thinking about a problem that you're kind of stuck on, and that's sort of happening in the background while actively you're working on revising a paper that's in sort of an editing process, and then you're doing something else with a collaborator. So there's sort of, hopefully you have enough going on that you can kind of pick up different things at various stages, and if you are stuck on one thing, think about something else for a while.
I've gone whole like weeks without doing anything in grad school, and then spent like 2 days straight just like working. Those bursts are very realistic. Way in the back, yeah.
I worked in the physical sciences and did some theoretical work. I can remember taking long walks. Do you do that sort of thing?
Yeah, actually, my husband, who's in the audience, went to grad school with me, and I would always get annoyed with him because we would be working on a problem, and then he'd go for a 3-hour bike ride and come back and say he'd solved it.
So long walks help, bike rides help.
Had he solved it?
Yeah.
It was a lie.
I always suggested that you should try that.
I know, I should have taken you up on it.
So one last question, and you've had your hand up a couple times, so I'm gonna pick you.
So how has the partition theorem changed our modern world?
So how has the partition theorem changed our modern world?
Well, in a practical way or in a mathematical way? Yeah, I mean, I don't, practically, I think the applications are still very theoretical, but it has been sort of kind of, that particular modular form has been kind of a testing ground for developing new theories in mathematics and new techniques that have been applied to other problems. So I think it's been very powerful in terms of driving new mathematics.
Like as a tool for, and then out of that will come something.
Yeah, so you sort of think something is true, try it out with partitions and see what happens, and then you prove something, and then you think, oh, maybe I can generalize this to a whole class of modular forms or something like that.
Awesome. So I think it is 7 o'clock, is it? Am I right? Am I good at telling time with my brain? All right, I want to thank you both for being here. That was super interesting, some of that stuff. Most of it I did not know. So I want to thank you, and thank you for your questions. So, and we're going to take this down and let you see the movie.